Thomson found the charge to mass ratio of the electron, and as a result was given credit for discovering the electron. But Millikan was the guy who actually found the charge of the electron. And then we combine the results of both of those experiments to find the mass of the electron. Millikan's experiment works something like this. We got two charged plates. One of them's positive, one of them's negative, although it doesn't really matter which one is which. That's caused by a battery here. Positive terminal of the battery, negative terminal of the battery. Causing the top plate to be positive, bottom plate to be negative. We inject oil droplets, microscopic oil droplets in between these plates, and we do something to these oil droplets. Maybe we expose them to X-rays to ionize them, whatever the case may be. We cause these oil droplets to become charged. Now, some of these oil droplets will become positively charged, and some of these oil droplets will become negatively charged. I want to focus on both of these for just a moment, and then we'll take a brief look at each of them individually here. The positive particle will experience two forces. Which two forces are they? Which two forces does the positive particle experience here? Yep. Good. The gravitational force and the electric force. The gravitational force will be downward, for sure. By the way, it's going to be downward on the other one as well, because gravity is always downward on a mass, right? What about the electric force, though, on the first particle? Is it upwards or downwards? Yep, it's downwards. The electric field is downwards, and it's a positive particle, so it experiences a force in the same direction as the field. Now, this one, though, experiences an electric force upwards, because it experiences a force opposite to the field, considering the fact that it's a negative particle. I want to focus on the particles right now that are suspended. Some of them won't be suspended. Some of them are going to accelerate upwards. Some of them are going to accelerate downwards, depending upon the values of each of these forces and the directions of these forces. But I want to focus on these particles, and specifically these ones where these forces balance each other, and therefore the particles remain suspended or travel at a constant speed. Here's the negative particle, where those two forces were in opposite directions. The electric force up, the gravitational force downwards. Now, they don't necessarily balance in every case, but if the particle is suspended or travels at a constant speed, then they're going to balance. We're going to say Fe is equal to Fg, and Q times E is equal to M times G. We'll rearrange that to get Q, and we get Mg over E. Millikan would have performed this experiment hundreds of times. He would have got hundreds of different charges of hundreds of different oil drops, and he would have found that they were all either 1.6 times 10 to the minus 19 or multiples of that, which led him to two conclusions, two aspects of a conclusion here. One, we have an elementary charge, a smallest possible charge, 1.6 times 10 to the minus 19. And that must be the charge of the electron as well, since that's the smallest particle that we know of. So we have the elementary charge, the charge of an electron. The second aspect of his conclusion was that charge is quantized, meaning that we can have a certain value, 1.6, or we can have a multiple of that, but we can't have 3.2 times that. We can have 3 or 4 times that, but not 3.2 times that. Let's take a look at the particles now that aren't suspended or traveling at a constant velocity. Okay, that could be this particle if the electric force is bigger than the gravitational force, or it could be this particle if the electric force is smaller than the gravitational force, or it could be this particle where both forces are acting downwards in the same direction and therefore can't balance each other out. Any way you look at it, if the forces don't balance, it's not going to be suspended and it's not going to travel at a constant velocity. In each of these three cases, we would set it up with the same way as we'd set up a question in physics 20, where we have unbalanced forces. F net is equal to the sum of the forces, Fe plus Fg. Now, if you were in physics 20, that's as far as you could go, because you don't know anything about electric force. But now that you're in physics 30, we can do some substitutions. We can say Ma is equal to QE, the electric force, plus M times G. And then we got to worry about negatives and positives. Okay. In the first case here, we'll make this case number 1, we'll make this one case number 2, and we'll make this one case number 3. In the first case, the electric force would be positive. The gravitational force would be negative. Gravity is negative because it's downward. The electric force is upward, so it's positive. And the acceleration, and therefore the net force, would be positive because the upward force is bigger than the downward force. In the second case, we would say gravity is still negative. The electric force is still positive because it's upwards, but the net force now, m times a, would be negative. Anybody tell me why? Why is the net force negative here? The m times a force, negative value? Yep. Good, because Fe is smaller than Fg. If the downward force is bigger, it accelerates downwards. Now in the third case, the force of gravity is negative because it's downwards, as it always is in this context. The electric force is negative because it's downwards. And the mass times acceleration force will also be negative. And we know that because if both forces are downwards, then the net force acting on it has to be downwards as well, therefore a negative value. All right? Now, the only other thing that I have to say here before we check over our homework is this. When you've got one of these problems, whether it's one of the first problems, like this where we find a charge, or whether it's one of these problems where it's a little bit more difficult to find the charge, draw the picture. Draw the picture. A lot of times you're given the value of the electric field, the direction of the electric field, the type of charge, the direction of a force. Draw the picture because it tends to, 9 times out of 10, simplify things. It helps you to get, 9 times out of 10, some piece of information that you might not otherwise be able to get. All right, we're going to take a look at those 2 questions we had for homework now, remembering, of course, that the answers that they give us in the book for both of those questions are wrong. We're going to solve both of these just because the answers in the book are wrong for both of them. Also provides us with a nice little review since I wasn't here yesterday to review this. Number 1 says calculate the net force on a sphere of charge negative 5e. What does that mean, negative 5e? Yep. 5 times the elementary charge, yeah, which is like 5 electrons, right? It's negative, so it's 5 times negative 1.6 times 10 to the minus 19 coulombs. Here's the mass. It's placed in an electric field that's upwards in a vacuum chamber. We want to find the net force. So we don't know that it's suspended. If it is suspended, then we're going to get a net force of 0. If it's not suspended, then we're going to get a net force of something other than 0. Let's draw the picture here. We've got a negative charge. We know that we have a downward gravitational force. We don't know which way the electric force is right now, but we know the electric field is upwards. If the field is up and it's a negative particle, then which way is the force? Cassie, which way is the force if the field is upwards and it's a negative particle? Good, the force is downwards. Now, when they did it in the book, they assumed the force is upwards, and that's what gave them that value of the net force. We know that the force is downwards because a negative particle has to experience an electric force opposite to the direction of the field. This is a positive particle, the force would be upwards on it. All right, let's say F net is equal to the sum of the forces. And we're just looking for F net this time, not the acceleration, so we won't even sub in m times a for that. So QE is equal to our QE plus mg. Q is 5 times the elementary charge, so 5 times 1.6, I think that's 8. Negative 8 times 10 to the minus 19. The electric field is 1 times 10 to the 5. The mass is 2 times 10 to the negative 14. And G is 9.81. Both of these forces are downwards, so we're going to stick in negatives in front of both of them. And when we do the math for that, we end up getting 2.8 times 10 to the negative 13 newtons. It's actually a negative value, which means it's a downward force. Notice a couple of things here when I did this. Number 1, I knew that this electric force is downward, and to make it a negative value, because I drew the picture. Okay, I suspect the people that wrote the answer key for this book didn't draw the picture, and they just looked at the field upwards and made that force upwards as a result of that. If we draw the picture, it's easier for us to see that that force has to be downward and get the right sign for it. Secondly, notice that I didn't put the sign of the charge in there. It is -8, but I didn't put that in there. I made it 8. I always drop the sign of the charge when I'm plugging into an equation, right? There's a negative in front of it, but that's indicating direction, not the type of charge. It just so happens that there's a negative in there, and it kind of looks like it goes with the charge, but it doesn't. Okay, it goes with the force. It's a downward force, so it's a negative force. Yep. They didn't make them both positive. If they made when they did their answer key here, they made the electric force positive and gravity negative. So that means they got. If they had made them both positive, they would have got the same number. It just would have been upwards, right, instead of downwards. All right. In question number 2, it says calculate the acceleration of the sphere if the direction of the electric field in question 1 is reversed. So let's draw the picture again. We know it's a negative particle. We know we have a downward gravitational force. We know we now have a downward electric field. Now, what direction of force do we have this time? It's a negative particle in a downward field. The force must be, Gordon? Upwards, opposite to the direction of the field. So we're going to say the electric force is upward. This is what they did in the first question, not the second question. So we're going to say F net is equal to the sum of the forces. This time we're going to say M times A is equal to the sum of the forces. And we sub in our numbers. Okay, we make sure that when we sub in those numbers, this value becomes positive, this value becomes negative. We solve for the acceleration, and I can't remember what it works out to be. I want to say 3 or something like that. Okay, actually that does ring a bell. -5.81 meters per second squared. That makes sense, right? It's downward, but if it's downward with an upward force, it can't be bigger than 9.81. Right? If you've got one force up and one force down, you have to have an acceleration less than gravity because something's countering gravity. It's just not strong enough to completely counter gravity, that's all.